Hi everyone. Well, this video isn't going to be very long. It will only take momentum. Ha 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 ha. No, actually, it's going to be pretty long because this is a long and hard topic. So let's get started. Um, Today we're going to learn what momentum is, and I think you've never seen this before, but it's actually something that's related to how hard something is to stop, and it's defined like this. Now, without further ado, we define momentum, which is this p thing over here, and remember we have a little arrow here because this is a vector. Now, momentum is defined as simply the mass of a body times its velocity. So this means that this is a vector that has the same direction as the velocity and is multiplied by the mass. And this gives us an idea of how hard something is to stop. So for example, if something is going really fast, it's really hard to stop. Therefore, high velocity, high momentum. But it could be that something is not going so fast, but it's huge. And it also makes it very, very hard to stop. And again, high mass, high momentum. So the higher the mass, the higher the velocity, the harder this thing is to stop, and therefore the higher the momentum. Now, what are the units of this? Well, the units, we can work them out by looking at the units of mass and the units of velocity. So we know that if a quantity is this times this, then its units will be these units times these units. So let's write that down. Now remember, this means units. So units of momentum will be equal to units of mass. So units of mass times units of velocity. And remember, this little point means multiplication. Sometimes I will use this instead of a cross because crosses look like X's. So when we do physics, we normally use a point for multiplication, but never mind. Anyway, and then we know that the units of mass are kilograms and the units of velocity are meters second to the minus 1. So these are the units of momentum, kilograms times meters times second to the minus 1. Now, momentum is actually really important, a really important quantity in physics. It's so important, in fact, that in modern physics, there's an equivalence between momentum and position, which means that we could be living in a universe, for example, where instead of positions, we had momentums, and position acted as a momentum, and everything would look exactly the same. So nowadays, we consider momentum to be as important as the position of a body. They're like dual quantities. They're related to each other in a very strange way. So I can't stress enough the importance of this quantity. Momentum is fundamental in modern, and of course in classical physics, but especially in modern physics. Now, it's also important because it allows us to rewrite Newton's law in a way that works always, even for things like general relativity, which we will talk about at the end of this course. So remember that we knew that force was equal to mass times acceleration. Now, this doesn't always work. And the reason this doesn't always work is that sometimes mass is not constant, but it changes. For example, if I have a bucket full of water and this water keeps evaporating or leaking, this mass is not always the same, and therefore I can't calculate this anymore. Now, I can fix this, and the way to fix it is to do this. Well, acceleration is just the increase in velocity per unit time, so I can rewrite this as mass times the increase in velocity per unit time. And then, since mass is constant in here, because we were assuming this when we wrote this equation, otherwise, as I said, it doesn't work, then we can say that the mass times the increase in velocity is the same as saying the increase in mass times velocity. So we can rewrite this as the increase in mass times velocity per unit time. But this thing here is just the momentum. So what we can really say, and sorry I forgot the little arrows for my vector, so let's just put this here. So we can just say that this is the increase in momentum per unit time. So we can rewrite Newton's second law as force equals the increase in momentum per unit time. And this is actually the version of the second law that we use nowadays. Because, for example, things like relativity, when a body is accelerated, its mass automatically increases because its energy is increasing and its mass and its energy are the same thing. And therefore we can't use this equation, but this one still holds up. So this equation is valid for Newtonian mechanics, but it will also be valid in the future. And this is also really cool, because if we know the force acting on a body and the time that it acts on this body, we can also figure out how much its momentum has increased. And if we know how much its momentum has increased and we know its mass, for example, we can figure out how much its velocity can increase very easily. So this formulation here is extremely handy for handling kinematics problems. Now, I'm going to use the quantity that we just derived, this new equation, to define a new quantity that I'm going to call impulse. And to do this, all I'm going to do is move this thing here over here. So multiply both by increment of t, so that it disappears here and it's multiplying here. And then what we get is f times increment in t is equal to increment in p. Done. Well, this thing here, f times the increment in t, we call impulse, and we express it with an I. And its units are, of course, the same as those of momentum, because this is just the increase in momentum. So, for example, imagine that I have a ball here, and its mass is 2 kilograms, and it's still. And then I do a force of 4 newtons on it during 2 seconds. So I want to know how much its speed is going to increase. So let me just write down here. So how much did its speed increase? Well, what I do is, first thing, I figure out the impulse. So how much is the impulse? The impulse is the force times the time. So 4 times 2. So impulse equals 4 times 2 equals 8 newtons second. And this is equivalent to kilograms meters times second to the minus 1. Because remember that the Newton is a compound unit. Okay, so this is my impulse. And that's equal to the increment in momentum. Therefore, what I have is that, let me zoom out. So then what I have is that the increment in momentum, which is the increment in mass times velocity, and since the mass is constant, it's just mass times the increment in velocity, so mass times the increment in velocity has to be equal to 8. And since I know that the mass is 2 kilograms, then all I need to do is that the increment in velocity is 8 over 2 equals 4 meters per second. So you saw what I did. First, I calculate the impulse. I use this to calculate the increase in momentum, which is just the impulse. And then if the mass stays constant, all I need to do is isolate the velocity. If it doesn't stay constant, then I need to figure something out. Now we're going to talk about momentum conservation. And every time you see this word conservation, you should know exactly what this means, because it's something that we use in physics at all. When something is conserved in physics, it means that it stays the same. So for example, energy is conserved means that energy is always the same. It doesn't disappear, it's not destroyed, it's not created. Same thing happens with momentum. Momentum is conserved, means that momentum at the beginning in a system has to be equal to the momentum at the end in that system. Now, when a physicist discovers a conservation law, they get extremely happy, start jumping in their chairs, because every conservation law makes our lives way, way, way easier than they were before. Doing things by kinematics, using acceleration and velocities and things like that, is a pain. Normally, we either use energy or momentum conservation to solve our problems, because it's way faster and it's way easier. So this is why this is extremely important, and you need to know it very, very well. If you try to solve problems using kinematics, you're gonna go nuts. If you use momentum conservation, you can make some things that are extremely complicated into extremely easy to solve problems. Now, momentum conservation only applies when I have a system. Now, what do I mean by a system? Well, a system is just a bunch of stuff put together. Okay, so got a bunch of little balls, different masses, whatever. Now, this is a system. It's just a bunch of things that I decide make some kind of set. And I say, okay, this is a system. Now, momentum is conserved, but only in a system where there's no external forces. So this thing is isolated. I can't, if I come in from outside and I hit one of these balls, then momentum will not be conserved anymore, and there will be some impulse, and of course there will be an increase in momentum. But if I don't touch this system and I just leave it to its own devices, momentum will be conserved. An example of a system where momentum is conserved is, for example, a bomb. So I have a bomb, I have this device, I'm not touching it, I'm not doing anything to it, and there's a reaction inside of it, and then fragments just fly in all directions. But nothing external touched the system, which means that the momentum of every single one of these pieces has to stay the same. Now, we're going to do a very simple example so that you can see exactly what I mean by momentum conservation. Imagine that I have two balls, ball number 1 and ball number 2. Now, ball number 2 is still and has a mass of 2 kilograms. Ball number 1 is not still, it has a speed of 2 meters per second, and it has a mass of 4 kilograms. Yeah, let's make it 4 kilograms. Alright. We wish to know what's going to happen when these two balls collide. Now, the first thing that we need to realize is that in this system, there's no external forces. I'm not touching anything. This is like a pool table. This is moving towards this. This is going to hit that. Something's going to happen, but I'm not touching it. I'm not doing anything to it. So it's an isolated system, means that momentum is conserved. So the first thing that I do is to calculate the momentum, the initial momentum of the system. So let's do that. First, I'm going to zoom out and put this a little bit up. Now, first thing, I'm going to calculate the momentum of this ball, then of this ball, then I'm going to add them up, and that will be the momentum in the system. So the momentum of this ball is going to be just 2 times 4. So it's going to be 8 kilograms meters second to the minus 1. And the momentum of this ball over here is going to be 2 times 0, because it's not moving, so the velocity is 0, which means that it's 0 kilograms meters second to the minus 1. So what is the total momentum of this system? Well, the total momentum is just the sum of both momentums, so it's 8 plus 0, that's 8. 8 kilograms meters second to the minus 1. And what does the law of momentum conservation say? Well, what it says is that once these two things have collided, since there's no external forces, the total momentum has to be the same. Now, what I'm going to assume is that these two balls collide and they stick together, so that they start moving at the same speed. So after the collision, this goes to both balls moving together at a certain speed that we don't know, and we know that the total mass is 6 kilograms. Okay. So what's the total momentum after the collision? Well, the total momentum after the collision will be equal to the total mass, which is 6, times the velocity that we don't know, and because momentum is conserved, it has to be equal to 8 kilograms meters second to the minus 1. So this has to be equal to 8. Now all we need to do is solve this equation that we do just by bringing the 6 over here under the 8. So then we get that V equals 8 over 6, which is equal to 4/3 of a meter per second. So this is how we use momentum conservation to find out for example, the final velocity after a collision in a system. This can be applied to any kind of situation, but the idea is always the same. I have a certain system, there's no forces at the beginning, there's no forces at the end, I don't touch the system, something happens, but we know that momentum has to stay the same. So we calculate the momentum at the beginning, we calculate it at the end, and we solve until we find whatever it is that we want to find, using the condition that the momentum at the beginning and the momentum at the end have to be the same. Now, believe it or not, momentum conservation is not a law, but it's a consequence of a law. It's actually a consequence of Newton's third law. And remember that Newton's third law says that if I have two bodies A and B. So this is A, this is B. Remember that the force that A does to B, for this force, there will be an equal and opposite force that B will do to A. And because of Newton's third law, momentum is conserved. And I will show you how this works. Now, imagine that I have, again, these two balls, and I know nothing about the velocities or whatever. It really doesn't matter. So this ball is going over here until it hits this ball over here. It will do some force to it. This one will also do a force to it. There will be a change in momentum, and we want to know what the change in momentum is going to be. Okay? So the initial momentum will be just the mass of ball A times the velocity of ball A plus the mass of ball B plus the velocity of ball B. And then the change of momentum will be given by the force times the time. And since this is a collision and they're in contact at the same time, the time that this one hits this one is the same time that this one hits this one, right? So what will be the change in momentum of ball A? Well, the change in momentum of ball A will be this force that B does to A times the time that the collision happens, right? Because remember that the impulse, which is force times time, is equal to the increment in momentum. So I'm going to write that, and I'll say that's equal to force that B does to A times T. I don't know T, but I don't care. And similarly, the increase in the momentum of ball B will be the force that A does to B times this same time. So F that A does to B times this same time. But remember that these two forces are equal but opposite. So I can actually write this as minus F that A does to B times the time, because according to Newton's third law, these two forces are equal and opposite. So now I want to find the total incrementing momentum, and the total incrementing momentum will be the incrementing momentum for ball A plus the incrementing momentum for ball B. So this plus this. And you can already see that when I do this, the incrementing total momentum will be A incrementing momentum of ball A, incrementing momentum of ball B, and that's just minus force A, B, T plus force A, B, T. And you can see that these two things are equal and opposite, so they go. So that's equal to 0. That is, the total incrementing momentum for these two balls is 0 because of Newton's first law, that this force has to be equal to this force. So again, momentum conservation is not a law that's fundamental. It is derived from Newton's third law. Now, unfortunately for you, all this momentum conservation stuff can be used to collisions in 2 dimensions. And what I mean by this is that, well, before we just were constrained to 1 dimension, right? This thing hits this and then this moves this way. But actually in real life, what normally happens is that this thing hits this one, and one moves this way, the other one moves this way. So we've got not only a horizontal component, but a vertical component to the movement. For example, when we play pool. Now, the good news is that this can be very easily solved using momentum conservation. All we need to do is do things twice. So once for the horizontal axis, once for the vertical axis. The bad news is, of course, that we have twice as many equations, and we could even do this in 3D, but fortunately for us, any collision that happens, even if it's in 3D, can be turned into a 2D collision like this one. Okay, so in this case, we've got this ball here, that's 4 kilograms, and bumps into the still green ball, and then after the collision, one goes this way, the other one goes this way. And what we need to do is to split our momentum conservation into the x and y components, and then just apply that twice. So that's what we're going to do. Now first I'm going to do the horizontal component, then I'm going to do the vertical component. Now for the horizontal, the initial momentum is just the momentum of this ball here, because this one has 0 velocity, so 12 times 0, that's 0. So the initial momentum is just the momentum of this thing here. So momentum at the beginning, horizontally, so let's just write x. So, whoa, that doesn't look too good, does it? Let's just write a little better. So the initial momentum in the x direction is going to be equal to 4 times 12, and that's equal to 48 kilograms meters second to the minus 1. Good. And we know that this has to be equal to the final momentum in x. We just don't know what the final momentum in x is going to be like. So the next thing that we need to do is figure out what the final momentum in x is going to be. And we need to do this by using trigonometry again. So how do we figure out the x component of this velocity? And again, it's using trigonometry. If you still don't know how to do this, then you're in serious trouble and you need to come and see me. So anyway, here's our velocity. We want this component here. This is the angle, that's 60. So I ask you, shall we multiply by the sine or the cosine? Remembering that this is the projection, it's like the shadow. I hope you just said, it's the cosine. Yes, we need to multiply by the cosine. So if we want to get this component here, we multiply this velocity that we don't know by the cosine. And this one, same thing. If we want to get this component here, we also need to multiply by the cosine. But of course, there's different angles. I'm going to call this velocity v1 and this one v2. So let's just say v1 and v2. And v1 and v2 are the total velocities, not the components, but the total. So let's see what we get. We get that the final momentum in x is going to be v1 times the cosine of 60 plus v2 times the cosine of 30. And these two things here are just numbers. So they're very, very easy to get. I'm not even going to bother calculating them, but be aware, we have two unknowns. This has to be equal to 48. We have two unknowns. We need another equation if we want to find them. And of course, the other equation is going to be the momentum in the y direction. Now what happens in the y direction? Well, in the y direction, what happens is that there's no momentum. This has no y speed. It's just moving horizontally, so the y momentum of this ball is 0. And of course, this one has no speed whatsoever, so the y momentum of this ball is also 0. So that makes things very easy for us. We got that the initial momentum in y is equal to 0. And it also has to equal the final momentum in y. And how are we going to get the final momentum in y? Well, the same way we got the x momentum, but this time, what do we need to use if we want to get this component? Sine or cosine? I hear sine, sine. Yes, the sine. So this has to be equal to v1 times the sine of 60, and this one will be equal to v2 times the sine of 30. So 0 has to be equal to v1 sine of 60 plus v2 sine of 30. And now we're done. I'm not even going to bother solving this equation. We've got two equations, this equal to 0, this equals to 48, with two unknowns, v1 and v2. So this is straightforward if you've ever done systems of equations. If you don't know how to solve a system of equations, then again, we're in trouble at this stage. Come and see me. Let's make sure that you learn how to do this before it's too late. Okay, so we're done. This is what you should be able to do after watching this video. You should know what momentum is and be able to define it. Remember that when we define things in physics, we use mathematical formulas. We don't use words. You should also be able to state Newton's second law in terms of momentum. So remember, not equal to mass times acceleration, but equal to the increase in momentum per unit time. You should be able to define and calculate impulse, which remember is just the force times the time. And then you should be able to derive the law of conservation of momentum using Newton's third law, which I just did. But you should be able to do this yourself. So please try it on your own. And finally, you should use momentum conservation to solve problems. Now, I can't stress how important this is. I can't stress this enough. This is key in your physics education, and every time that you see a problem in an exam that looks like it involves kinematics of some sort, the first thing you need to ask yourselves is, can I solve this using momentum conservation? And if the answer is yes, just go straight with that. If the answer is no, then ask yourself, maybe I can use energy conservation. And if the answer is no, then maybe you go ahead and use kinematics. But always, always, always prioritize momentum conservation and energy conservation over any other way of solving problems, because this is going to make your life a lot easier. Okay, now there's lots of problems this time. Lots and lots and lots of them. Most of them are compulsory because I think that this is a very important topic, this and the next one. Just do as much as you can and make sure that you really, really nail this topic. This is very, very important. Good luck.